Hello everyone, and welcome to the R&D Talk. That's the series where researchers and research enthusiasts share the interest on the latest technology and its practical application in the industry. Today we'll have the topic about artificial intelligence. There are three layers of AI, let's say, competency. First one, when you just take an API and build your own solution based on that. That's a really good format for POC, and most of the teams use that and starts there. Then we have second level, let's say, when you create a custom pipeline combining different tools and focus more already on the scalability and efficiency. And then the last, let's say, level, maybe not least, for sure, is when you train your own model, fine-tune that model to make it even more efficient and specialized. We are really glad to have the experts across all the line, and today we'll focus more on that, the most advanced stage, where the speakers share the experience, how to train and fine-tune foundational model on a cluster of GPUs like they did at DGX Cloud. So let me introduce our speakers. First is Taras Rumezhak, our vision practice leader. He has 5 years of experience in commercial research and artificial intelligence, specifically with the focus on computer vision, generative AI, and responsible AI. He has strong academic background, as well as studying in University of Oxford and Ukrainian Catholic University, and published number of cutting-edge researchers over the past years. The second speaker is Mykola Vysotsky. He's a researcher in our R&D department. He is currently studying at Ukrainian Catholic University and work mostly at the computer vision and generative AI type of tasks, while combining the academic research with the practical business innovation application. So the topic will be really exciting, and I let the speakers to share much more. But just a reminder that you will have the chance to ask the questions. All of those questions, based on the time availability in the end, will be answered on the Q&A session in the end of the talk. And also, in the end of the talk, you would expect one announcement. So please stay until the end to be aware of all the latest updates in that direction. Taras, pass word over to you.
Yeah, hey everyone. Thanks, Bogdan, for the introduction. And I'm starting to share the screen. Let me know if you can see the presentation.
Yep.
Awesome. So let's start with the agenda. So today we will start with the introduction. Why we are doing this, what is motivation behind the training some foundational models. Then we will have introduction and description of the DGX Cloud, what it is, why we need this, and how helpful it was. Then we will start with the most interesting topics. So our three main experiments on DGX Cloud. So the first one is the control net, which was the easiest one to replicate. Then the second one is the harder one, is to generate a distilled version of the model. And then we will talk about Olympus, our own foundational model that we had a chance to train on DGX Cloud. And after that, you will hear some announcements and some interesting stuff. So stay tuned. Bogdan already had a great introduction of the speakers. So let's straight jump into introduction. So no worries, it will take 5 to 10 minutes just for you to understand why we are doing this. So we are from the research and development department, and let me explain you slightly the landscape of our work. So we have, and this is my personal identification as I say this, so we have the three main pillars. The first one is commercial projects, the second one is foundational and applied research, and the third one is products. So of course, like commercial projects, it's a part of development. Research, it's the part of research, but as well we have our products which we are selling to the customers, and there are some public case studies, so you will be able to hear more about those. Now let's understand deeply the vision practice directions. So that's the part that we are working on. So we have some projects in direction of image generation, video generation, image analysis, video analysis, and some part of visual agents that we started working on recently. So those are the main directions. And if you have something relevant to those expertise, just contact me or Mikola. Let's start with the customer problem example. So we had one of the residential real estate companies that required a video generation pipeline. So what they're working on? They have a lot of properties which are empty, and they want to create some commercials for those properties. And of course, seeing commercial with just like empty room without no life within that, it's not impressive. So they asked us to generate videos, but populate it with real people, with the furniture, etc. And we started using some of existing models and tried to use like stable diffusion in painting and alternatives just to generate the image like this. But what's the problem with this one is that it doesn't preserve the original structure of the room. So we cannot have the desired result with the existing models. So the example of our own model is highlighted here, where we are presenting the preserving the original room, but still populating it with people and furniture, which was the desired effect by the customer. So just a high level of review of the commercial models. So uh, in a lot of the projects, so for example, in some other companies, my friends, etc., within startups, the people are heavily reliant on tools like ChatGPT, like DALL-E, Midjourney, Firefly, etc. And there are some pretty good advantages of using those. And those are mostly related to the commercial usage and IP ownership. Because when you're using those models, you're just paying the fee and the responsibilities on their side, on the training data set, etc. But there are like very important problems, like the pricing, of course, and the control for that model. So you're limited with what those models can achieve. And recently, people started using ChatGPT image generation a lot, and it's good. It's a significant improvement, but still, it's not accurate, and sometimes pretty often, it might give you unexpected result, and you have no control of adjusting it according to your needs. So on the contrary, there are some open source models which we have control on. And the most common one is Stable Diffusion XL. So that's the basis for the majority of the projects because it's fully open source, it allows commercial usage, and you can adapt it, and there are a lot of community adapters to it. There are some other models like Flux, but this one it's open source, so you understand how it works, you have access to it, but you don't have the right for the commercial usage. And there are a few more that are pretty common for our usage. It's Janus Pro and Hydream. So Janus Pro is from DeepSeek, and this Janus Pro was actually the basis of our main Olympus model that we will be talking about today. So just to recap, the problem with commercial models is the price and lack of control, while the problem with open source models is that sometimes they are not allowed for commercial usage, and if they are allowed, sometimes like Stable Diffusion XL, it might be outdated, and there is a lot of room for improvement. So next, I would like to introduce you to another part of motivation of the development of models. It's the product part of our R&D department. So this is content creator. This is our product that allows you to work with different use cases. So here on the video, you can see the use case of creating some stickers to put on the products. So you're generating everything with the prompt, and there is like a way to adapt it due to the brand book, to some specific set of rules, etc. But another use case is to generate the LinkedIn or Facebook or any other social media banner. And so firstly, we generated a sticker that you can print and put on your product, and then you can generate the whole banner for the LinkedIn post, for example. And here you will see how it looks like. And originally, we are utilizing some of the open source models and some of the commercial models for this product. But this is probably going to change. Highlighting everything mentioned, we have three main goals. First one, support customers. Second one, write research papers. Third one, develop in-house model, for example, for content creation that I've just shown. And the topic of today's presentation is actually to kill two birds with one stone, but actually three. So with today's presentation, the models that we've developed, it solves all of the mentioned problems, and we are actually achieving all of our three goals. I will tell you another example. This is our SketchUp project. We started on working on PBR materials for rendering for 3D objects, and it's a public case study. Client is satisfied, but internally we started doing research around this topic, and this research helped us to achieve all of those goals. So client is satisfied and research is done. We actually published two posters on NVIDIA GTC, and we have two papers, one accepted last year to ECCV, and another one about slightly different topic is accepted to the CVPR this year and will be presented like just in a few weeks. But there is a serious problem with this. Why that successful example might be harder to scale to the new challenges? It's because of the lack of computational power of those precious GPUs. So, for example, Stable Diffusion XL, it took more than $500,000 to train Stable Diffusion XL, which is outdated right now. And it used a lot of GPU computational resources. Here you can see some numbers, and that's pretty expensive, and it's hard to achieve such a quality. But here is actually a solution that helped us to resolve this problem. So we had access to the NVIDIA's DGX cloud. And let me as well give you a very short overview of what is DGX cloud. So actually it's a supercomputing AI service and it's a unified platform where you can get access to some of the computational resources, where you can train models, fine-tune those, and with an easy way to access those and to manage on DGX Cloud instead of working with on-prem management with your own solutions. Here you can see a general overview of this. So the part of DGX Cloud, there are some NVIDIA AI experts that will be able to support you with some needs. There are as well some pre-existing services that might help you on hosting existing models from NVIDIA AI enterprise part, or benchmark models, or do the serverless inference like post-training, etc. There are some specific optimized GPU and storage computational resources, which we were actually using. And just to give you an overview, on what we've used for our experiments. So we used a cluster of H100s GPUs. We had 4 GPU clusters, each containing 8 H100 GPUs, and we spent like around 3 months of training. And each GPU, depending on how you can calculate it, but just for the understanding, it had like 80 gigabytes of GPU of video memory. So that's not like a supercomputer used for like chat GPT level training, but still it's a pretty good set of resources to satisfy our needs. Here as well, a few more comments on the NVIDIA DGX Cloud Create part. It's an introduction for the next couple of slides, how easy it is to use, to set up the experiment, to set up the storage, and the core component of it is like actually a workload optimization and orchestration and just management of everything via NVIDIA Run AI platform. And I will give the word to Mykola to describe some details about this platform and how we use this.
Yeah. So first of all, what is NVIDIA Run AI and why? This is a platform that's designed to orchestrate and optimize some workloads on clusters of GPUs, and it works upon the NVIDIA DGX infrastructures, and NVIDIA infrastructure and its cloud service providers. So for us, it was like a very comfortable platform to perform all our experiments. And next slide, please, Ross. Yeah. And now I want to describe how easy it was to create tasks for our create several cloud tasks for our solution. So we use the very comfortable GUI interface. So what you need, first of all, you just initiate the project. After that, you need to set up the environment. It's very easy. You can just everything you need is to just select the container from which you will start the job. Maybe optionally you can add some tools for some tools you want to use. For example, if you want to work interactive, you can add something like Visual Studio Code or just Jupyter notebooks to work with this. After that, you need to define your workload type. It could be, there are 3 types of workloads. So first is for training, second is for inference, and another is for interactive usage. After that, you just need to select allocate the resources you want to use. So this might be GPU counts, RAM, number of CPU cores, or something like persistent storage PVC. And after that, you just have to wait actually like for a few minutes to workload to start. And after that, you can perform all your experiments, run your code, training, inference, interactive usage, etc. Yeah, and so now I want to talk about our first experiment, which is training our own control net model. So for introduction, why we do this? Because while working in R&D, a lot of our projects requires a controllable image generation controllable by form or structure, and so we decided to train our own control net model on semantic segmentation masks. But we had one problem, which is there are no high quality data set for semantic segmentation available right now. There are some outdated data sets with very low quality images, low resolution, and like this. So we had a solution to create our own data set, which is semi-synthetic. So what we did, we take high quality images from Lion Aesthetics dataset and created our own segmentation masks and text captioning for these images. So, yes, so and for the segmentation, we used lightweight models like mask former for mask generation and visual language models like Qwen2VL to be instruct for generating the text captions. Why we use these models? Just because if you want, if we don't want to pre-process dataset, but make this make captioning and segmentation mask generation on fly while training the model, controlled model itself, we need these lightweight models to fit in our GPUs. And so on this slide, you can see the high-level pipeline of our generation, of our training. And the training was performed on, for this experiment, it was performed on 8 H100 GPUs using the Accelerate framework. And why we use this Accelerate framework? To distribute our training over those GPUs to gain the peak performance, to gain the as good performance as we can. And how it works. So actually just each GPU have its own training setup. So each GPU have its model and also all additional models that was mentioned in previous slides. And training is replicated on every GPU, and just in when we need to synchronize the gradients to update model weights, the results from the GPUs are gathered, and the model weights are updated for every GPU, and this training repeats. Also on the slide you can see some technical details of the training, such as batch size, mixed precision, and number of steps that it was trained. Yeah, and on this slide we can see some results. They are actually pretty good. Yeah. So our next experiment was the distillation of Flux dev model. Yeah, and why we do this? Flux dev, in its time it was a SOTA image generation model, and this model, it takes like very long time to generate image. For example, it could be like up to 2 minutes, as it takes a very high number of the sampling steps to generate the images. It's like in range from 40 to 50. And to faster the image generation, they also released their own distilled model. It's the distilled version of FluxDev, which is Flux Schnell, and everything was great. So like they released their pre-trained model weights, released the model demo on the Hugging Face Space, also released inference code. Everything is great, but they didn't mention anything about the distillation process itself. They didn't mention any train code for this, and didn't describe the algorithm anywhere. And so we decided to get this experiment. And why? To reproduce the results and understand how this works internally, to gain to gain expertise in such tasks, as they might be helpful in future, for example, for our clients or for us itself. And also it allows us to customize the training process for our specific needs. And that's why we tried and actually succeed to build our own distillation of this model. Yeah, and now I want to describe on high level how this algorithm works in simple words. First of all, in our setup, we have two models, two copies of one model. One is teacher and second is student. So teacher is an original FluxDev model, which takes 15 steps, for example, for generating image. And student model, it's copy, but it is trained to generate same image in half less steps than teacher model. And how it do this? On this slide you can see that for 2 teacher steps, sampling steps of image generation, our student model is trying to do this just in 1 step, so skips 1 intermediate step. And in this manner the student model is trained to generate image in, for example, if you have 50 for teacher, it will generate student will generate image in 25 steps. And this was the basis for our distillation strategy. But why to limit us with only 25 steps? We can go deeper and, for example, repeat this same experiment, but when our student model becomes a new teacher, and we train new student to take also half less steps, as you can see on this slide. And like limit for this is only when we go to the one step image generation. Yeah, here you can see the short recap of this generation algorithm. So as I said, in our step we have teacher and student model. We initialize our student model from teacher model on the beginning. After that, there's more technical test. We sample timestamps, generate the images, noise latents on which we will train our student model. After that, we take 2 steps with teacher model, take 1 step with student model, and then just use MSE-LOS to train our student model. And after we repeat this process when we reinitialize a new teacher as an old student. Yeah, and for these tasks, we cannot do the same as we do for the control-led model, as we have 2 huge teacher and student model, each have 12 billion parameters, and so it's just we are not capable to fit our one training in one GPU. Even 80 gigabytes of RAM is not enough, and so we need some smarter way to distribute our training. And the solution we found is to use Torch fully sharded data parallel framework. It's like a cutting edge Torch framework, which is basically what it does. It can shard one model into few parts. Each GPU will have its own part of the model, and when we do a forward pass or backward pass, each GPU computes only its part of the model forward pass pipeline, and they all synchronize when needed. Also, as you can see on the slide, we didn't shard the models like YA or Clip. It's just because they are small enough to fit in each GPU, and it allows us to reduce the latency for this communication. And here you can see the results. First row is the original FluxDev 50 steps generation. Quite good results, absolute perfect. In second row, you can see the same model, but with 4 steps. It tried to generate something, but it was not trained to do this in such small number of steps. So you can see it struggles to generate high quality images, and they are just blurry, and they cannot be used. And on the last row, you can see our model, our distilled model, our distilled version of FluxDev model, which also takes 4 steps. But as you can see, the results are comparable to the FluxDev model in 15 steps. Like we can generate images with same quality, but basically in 10 times faster. And now we want to tell you about our last and most interesting experiment. It was our training of our own foundational model, which we named Olympus. So as Taras already mentioned, our R&D is based on the research foundation, and for this, why it's important to build our own in-house model. So it's first of all, it's our research foundation. After that, we have as we have our own model, we have like intellectual property on this model, and we can use this in any of our pipelines. Yeah. And now, what was our first idea? Recently, the Janus model was introduced, and what we were very excited to build our own model upon this architecture, and but with our own architectural solution and some refinements. And so what was our idea? Our idea was to just align the LLM's uh, internal representation from LLM layers with layers of the vision encoding model, which we hypothesize will help to somehow regularize its space, and to faster training, first of all, and second, to yield higher quality images in the end. And okay, next slide, please. And actually, we found out that this idea was great, but with one problem. It was published like 1.5 months before, and from this we found out that we have true hypothesis. Our idea was great, but already published. And also we mentioned that after careful reading of Janus paper, we found out that it was this research was already cited in this paper, and so this idea is cannot be considered as our own, and we cannot build our foundational model upon this. And after that, we had to develop a new idea, which looked like this. So on this slide, you can see that on the left, we can see the original Janus model structure, architecture, which consisted of encoder and decoder models, which were just some basically were just some convolution and up convolution modules. And what we decided to do, we decided to replace this encoder and decoder architecture with some more advanced more advanced architecture, like double stream and single stream blocks. So what is that, and what's the difference between the simple encoder decoder? So double stream blocks, it was actually takes the text vectors and image vectors and process them differently. So for each of these modalities, it has its own head, and this allows for more efficient encoding of the information for the space for the LM space. And the single stream block, main advantage of this is that it doesn't deny the textual vectors as it is in the original Janus structure, and thus we hypothesize it can help with prompt following. And yes, so after that our training was performed in 2 stages. So for the first stage, first of all, we take the original LLM back from the Janus model, and replaced with this encoder and decoder modules, our own encoder decoder modules with single stream and double stream encoder. And after that, first stage of training was the adapting of our own modules for this LLM internal space. You can see in the table, you can see some technical details about this training. And after this first stage, we trained the model longer for the second stage, where we unfreeze this pre-trained Janus LLM and train whole model to further train this, and further train this on the mixture of 2 datasets, one of which was synthetic DALL-E datasets with a high quality DALL-E dataset, and second was also a high quality Lion Coco dataset with already captions. And here in this slide, you can see quantitative results for our model training. So first is the user preference study. Here you can see that as we hypothesize, our prompt following is much better for our encoder-decoder architectures, and also visual aesthetics was slightly better, but that was not the main goal of our model training. And also on the right side, you can see some scores for some scores which also represent simulation study for our changed architectures. Okay, so I see the question in chat, how long did it take to train it? So basically, if not mistaken, it took maybe
Like
30 hours to train this for both stages.
let's leave the questions till the end. So if you have some questions, just ask those. We will answer those in the end.
And so yeah, so on this slide you can see some few examples of our model generation. So as you can see, like image quality is quite good, but it's comparable to the original. It's not like very high above the original Janus architecture, but you can still see a good prompt following. And Taras, can you next slide, please? On this slide, we see that prompt following is actually quite better for our own model than for original Janus. As you can see, for example, in this great pizza example, where our model took this prompt very much better than the original. So like on the right side, on the left side, you see the result from original Janus model, and on the left side, you can see the results from our model.
And just to comment here, so basically the outcomes of those three experiments, so as I mentioned in the introduction, so we had some customer problems. For example, that the generated room is not similar to the original one. So the in-painting of furniture and people is different. And we wanted to take some newer models, and we want to run to have a control on that, to integrate segmentation to this. That's why we've done the experiment with segmentation control net, experiment number 1. For the model distillation, some customers, they are requiring the faster image generation. And as well, for example, for content creator solution, sometimes it take a longer time to generate some images, and still like 20-30 seconds, it's nothing comparing to what the designer will spend on that. But when we are showing this, for example, on some conferences, etc., so waiting 20-30 seconds might be maybe like not that encouraging for the prospects. But having the models that will run like in 4 seconds, it's much more impressive and achieving similar results. That's what was the purpose of our second experiment, the distillation. And why we've done this, because as Mykola mentioned, the authors of the original Flux Schnell and Flux Dev, they haven't released the instruction and the algorithm that they've used to distill the model. So we've done this from scratch, and we've actually released it to open source. I will tell a few more comments about this in a few minutes. So that was the motivation for the second experiment. And for the third experiment, as I mentioned, the existing cloud infrastructure, it's not that impressive as, for example, the ones that can be used to train like GPT-like models, etc. And it's not capable of training some very significant and hard, complex models within that time frame with that computational resources. But we've done some tweaks and tricks, for example, reusing some of the pre-trained components. And we've trained the model that is comparable to the Janus, like the open source model allowed for commercial usage. So we have our own model that we can reuse on commercial projects within our products, and which is better than the existing Janus model. So and it's better in terms of prompt following. As well, prompt following is an important step here, and a lot of models are struggling with it. For example, Stable Diffusion 3, and I even had a post about this tutorial on LinkedIn. Stable Diffusion 3, it resolved the problem of prompt following. If you're comparing Stable Diffusion 3 and Stable Diffusion XL, Stable Diffusion 3 has much better prompt following. But you can use Stable Diffusion XL for commercial purposes, and you cannot use Stable Diffusion 3 for commercial purposes. That's the main issue. And now we have the Janus model, and a Janus model, it's good enough and it's allowed for commercial usage, but the prompt following was not that impressive. That's why we took the original model, we trained it for our need, for the better prompt following, and now we have the model which is on the quality level similar to the original model. So as you see, the images are not perfect, and as well as the training time was not enough. We might train the model longer, but we successfully resolved the problem of prompt following, and I believe that's an impressive result, and we can proceed with it to the next milestones. And based on this, we've as well prepared the research paper, and it's currently being under review for some of the conferences. We will dive deep into this topic, but what I want to show as well is a small sneak peek on Olympus series. So all of our experiments, like the 3 ones that were presented today and some that are in progress, they have like a common thing that they are designed to satisfy our needs, like to satisfy clients, to support our product, and to contribute to the research community. And we've decided that we will have this umbrella of our developments, and we call this Olympus series of models. So within this, we are collaborating with different teams within SoftServe. So for example, high-performing models. So not even in terms of 4 steps generation as the distilled version, but in terms of some hardware optimization, acceleration, etc. So for control net models, for different models, we are adjusting it not only for Flux, but for some other models, and we have this expertise, we can do this, we know how to do this, and we are sharing it to the open source community, the exact tutorial how to do this. Customized text to image, you've seen this. Text to video, that's something that requires much more resources, but we are working on this. And my favorite part is physical visual AI agents. So that's something that we recently started working on, and we have some of the first results. So just for comparison, we have a comparison of video generation result and physics-aware result. So this is like some car brand, and this is a result of image to video. Like for me, it's good enough result. Of course, like you can see that this is a generated video, but it's more or less. Of course, like the physics are not accurate in terms of the sky, in terms of the tree, in terms of the rotation of some elements, etc. But this is good enough. And what's the physics-aware part is this one. So what are we working on? And as you might see, so this is like dorms of Ukrainian Catholic University. and this is actually the basement of it. So there is no possibility to bring the cars there. But within our current research direction, within this Olympus series, we are working on this, and we are placing some 3D objects within existing videos. And for this, we have a lot of algorithms underneath to analyze the surface, to properly render it, to actually change all of the shadings. So for example, you may see how the sun from the window impacts the car, and all of the reflections are natural. This is only first intermediate result. That's our main focus right now, and I hopefully will share more results soon during next some future R&D talks. And another announcement, and it's just for you to have some hands-on experience, is that SoftServe is now on Hugging Face. So we are encouraging you to scan this QR code and go to our SoftServe page. We have deployed the distilled version of the Flux model, so you can visit there. You can type. Let me actually show you. So I am on the space. I'm just typing cat, and I encourage you to play with the sampling steps. So for example, on the presentation, we've shown the results with 4 sampling steps. So I'm clicking submit. We are generating the image, and okay, it's ready. We have 2 images of a cute cat. It generated in less than 4 seconds, maybe even 2. There might be like some workload on it, so there might be a queue, but it should work, and please experiment with that. Our next plan is to release as well ControlNet model, release the full white paper on the technical report, how we've done distillation, how we've done the training for the ControlNet, and the Olympus model, the main one that you've seen today, it will be released slightly later as we are under review for the research publication about this. So for now, we cannot share it publicly, but it will be available in the near future. So thank you. That's it. Now we are happy to answer your questions.
Yeah, thanks for the great presentation, Taras, Mykola. And I think it's even more exciting to see that we made that first steps into the open source while having the Hugging Face space where the people can actually test the trained model. So hope that there will be even more contributors from different teams while that approach with the model fine-tuning and training become easier and easier. So yeah, any more questions from the listeners and today participants? There was one question in the chat from Taras and a comment from Roman. So if you will have any more questions after that, just feel free to contact Taras and Mykola directly, either on Teams or via LinkedIn if you're watching externally. And we know that that's super niche topic, but I think that's good for you to be aware that we had such niche knowledge, and we hope that such kind of results will be even more and more democratized, and you can do that not only on the large cluster, but on our own maybe laptops in some near future. We have the question from Bogdan: how many parameters, if not a secret?
How many for each model? For which model?
Yeah, for the biggest.
Biggest, biggest is actually the flux distillation. It have 12 billion parameters.
12 billion. And so it's relatively, I mean, moderately costly to run, to train, not very expensive, right? Yeah. Makes
I mean, it's
sense.
still like a cluster, but of course it's like much less expensive than to do that
yeah, because if that would be 200 billions, I mean, it's still possible, but to run would be 10 times more expensive, and results will be only a couple % better, right?
So
I mean, it's from my point of view.
what do you mean, like more expensive for which one?
Yeah, as I understand, if 10 times more parameters, it would be 10 times the price to train the model,
Like
it's not the rule, but
approximately, like
roughly.
high level.
approximately. And yeah, but the performance gains will not be 10 times. It will be, I don't know, 5%, 10%, maybe even less.
It
Depends on the use case, of
What do you
course.
mean by performance? If it's like quality or
Yes.
so as well, it's so here we were accessing quality based on win rate. So we are showing two images of for the people. So within our experiments, we have 52 people who were assessing it, and so it's more or less actually the experimental setup for this. And it's hard to estimate like 10%, 10x improvement with such models. So it's probably impossible because still there are different preferences. It might be subjective.
Yeah, that's right. Yeah, experimenting with state-of-the-art techniques is very good. Yeah, thank you for showing us your good work.
Have you tried the Hugging Face?
A little bit, yes.
So
not much.
Yeah, expect more from us, sir. Thank you.
Thank you.
Thank you for the question, Bogdan. So, if there is no more question, thanks everyone for joining today, and looking forward for our next meeting in a month. See you. Bye-bye.
Thank you so much. See you. Bye.
Thanks, everyone.
Thank you.
Okay.
Bye. Thank you.